Convex hull, we're talking about the famous convex hull problem. Given n points on the plane, find the convex hull of those points. Okay. And what's the convex hull problem? It's commonly pictured as, given all the points, let's suppose those points are represented by nails, simply put a giant elastic band around it, and once the elastic band automatically contracts, it'll come up with the smallest possible convex shape around surrounding all those points. It'll be touching all the exterior points and not touching the internal points. So convex shape formally means that when there are any 2 points within the polygon, then any weighted average of those 2 points is also within the polygon. As an example, the 3 polygon shapes that you see up on the top, the oval, the square or the rectangle, and the pentagon, they're all convex shapes. But the L-shaped red shape at the bottom is not a convex shape, because when you see those 2 points that are connected by a line, all the points connecting those 2 points are themselves not within the polygon, and therefore that shape is not a convex shape. And we will be using our very familiar divide and conquer algorithm design technique, and we will following the similar protocol as what we used in the closest pair of points, that will simply divide the set of points into left hand side and the right hand side, recursively compute the 2 hulls, and then merge the 2 convex hulls by finding the upper and lower tangents. And this is our divide step. We will simply look at the x coordinate of the points, find the median, and at that point we have the dividing vertical line with half the points on the left hand side and half the points on the right hand side. We can then at that point do the conquer step, that's the recursive calls, which compute the convex hull for each half. Our base case can be that if you have only 2 points or 3 points, then you have a trivial hull. Otherwise, you keep making the recursive calls until you hit your base case. In the merge step, what we'll do is we will find the upper tangent connecting the 2 hulls, the lower tangent finding the 2 hulls, combine them to find the overall convex hull. When we say the upper tangent or the lower tangent, sometimes it can be perceived as we are asking you to find the 2 topmost points. That's not necessarily the case, as you see in this example here. The 2 northernmost points here, if you connect them on the left hand side and the right hand side, then you get this blue dotted line. But that's not actually the northernmost or the upper tangent here. And that's a small implementation idea that you have to keep in mind. But anyhow, the tangent can be easily found in big O of n time. It's a linear time, and similarly for the lower tangent, which gives you your desired time complexity, which is our familiar recurrence relation. T of n is equal to 2 times T of n by 2 plus big O of n, which leads you to T of n is equal to big O of n log n. Again, that's a familiar recurrence relation that keeps coming up again and again in many different divide and conquer algorithms. That's our conclusion, that the divide plus merge portion can take big O of n time, leading to convex hull being solved in big O of n log n time. Here's an extra note here, that if you are not careful with running your median and you do end up sorting the points to get the median, which makes it run at big O of n log n time, your time complexity doesn't really change very much. It becomes big O of n log square n, which is not necessarily the best. What's possible here, you can do big O of n log n. Incidentally, that's also not the best time complexity. The better time complexity by the famous Chan's algorithm is big O of n log h, where h is the number of points on the convex hull.